We have now covered some ways to graphically depict data and some key statistics that you all need to know about. We will next talk about normal data sets and the empirical rule. We then conclude this video with discussing correlation and causation. After playing with much data, you will come to realize that many of the large data sets observed in practice have histograms that are similar in shape. These histograms often reach their peaks at the sample median and then decrease on both sides of this point in a bell-shaped symmetric fashion. Such data sets are said to be normal. If the data set is close to being normal, we say that it is approximately normal. So in this particular case, we have an approximately normal data set. Now, compare the previous graph, which now is on the top, with the graph at the bottom. As you see in the bottom graph, the data values are not symmetrical around the sample median. We say that the data set is skewed. In this particular case, since the tail is towards the right, we say that the distribution is skewed to the right. Hence, it follows from the symmetry of the normal histogram that a data set that is approximately normal will have its sample mean and sample median approximately equal. If bar x and s are the sample mean and sample standard deviations of an approximately normal data set, then the empirical rule specifies that the approximate proportions of the data observations that are within 68, 95, and 99.7% lie within the sample plus minus 1, 2, or 3 standard deviations. We will now end this video by talking about sample correlation and the issue of causation. We are often concerned with datasets that consist of pairs of values that have some type of relationship to each other. Have a look at this table. Columns 1 and 3 list the number of lines of codes a class or a module has. That is, the first module has 21,000 lines of code. And in columns 2 and 4, we see the number of faults that were found in the development of that module. Note that there are more data values which we don't have the room to list here, marked with 3 dots. If we instead visualize the data in a scatter plot, we see the following. In the scatter plot, it appears to be some connection between number of faults and number of lines of code. That is, the more lines of code, the more faults. We would like to measure the strength of this connection, or in other words, the correlation. So let us next look at the statistic sample correlation coefficient, denoted R. If xi and yi are two paired data points and x bar and y bar is the mean of the x and y values respectively, and sx and sy the sample standard deviations of x and y respectively, then the sample correlation coefficient R is the sum of the x and y values minus the sample means of x and y divided by the size of the sample minus 1 multiplied by the standard deviations of x and y. Now, when R is larger than 0, we say that the sample data pairs are positively correlated, and when R is less than 0, we say that they are negatively correlated. Let us now look at the properties of the sample correlation coefficient. Property 1 says that R is always between -1 and +1. Property 2 says that R will equal +1 when there is a straight line, that is to say a linear relation between the paired data such that large y values are connected to large x values. Property 3 says that R will equal -1 when the relation is linear and large y values are attached to small x values. Finally, property 4 states that the value of r is unchanged when a constant is added to each of the x variables, or for that matter, y variables, or when each x variable, or for that matter, y variable, is multiplied by a positive constant. Property 4 indicates quite clearly that r does not depend on the dimensions chosen to measure data. That is, you can measure a person's weight in pounds or kilograms. The absolute value of r, that is, its value without regard to its sign, is a measure of the strength of the linear relationship between the x and y values of a data pair. 1 implies a perfect relation, i.e., the line passes through all data points. A value of 0.8 means that the relation is relatively strong, i.e., the line is close to them all. Finally, a value of, for example, 0.3 implies a relatively weak relation. The sign, that is, plus or minus, implies the direction of the relation. Now let's see what happens when we enter our data into a computer to calculate the R statistic. Entering the data in RStudio, which is a statistical software you can freely download, we calculate R. There is an accompanying video to this lecture with instructions on how to do this step by step. So, RStudio tells us that we have a correlation of approximately 0.89. And it is a positive correlation, i.e., the larger the class, the more faults there are during the development. 0.89 indicates also that the linear relation is relatively strong. So what can we say from this? Well, we only had 32 pairs, so there aren't that many data pairs, and the values might have come only from one project using one particular programming language, maybe even having inexperienced developers. In short, just because we see a correlation, that does not mean that one causes the other. That is to say, that lines of code are directly connected to the numbers of faults found. Hence, the golden rule to always remember and to always say the last thing you do when you go to sleep is: correlation does not imply causation, meaning we cannot assume that one causes the other. We might have a case of causation, but again, we cannot really tell by the statistic R. Correlation simply measures association. We have now concluded the first video in the statistics module. I do hope that you study these basic concepts and know them by heart. The next video will cover the basics of probability, and we will introduce concepts such as conditional probability. We will also discuss and present basis formula, random variables, expectation, and variance.